Hi, my name is Jonas Urbanas. I'm a senior product engineer with Mori Microwave, and I'm very excited to present to you our millimeter wave vector receiver load pull solution that can be configured to perform high power hybrid active load pull measurements up to 110 GHz using our IVCAD software platform, our custom signal control unit, and 110 GHz low loss couplers with integrated down conversion. Load pull measurements have long been used to characterize microwave transistors and power amplifiers under large signal operating conditions, and with emerging millimeter wave radar applications, the ability to perform high power load pull measurements at W-band is now more important than ever. Load pull measurements are performed by presenting a set of controlled load impedances to a device under test while measuring a multitude of device parameters at each impedance state. There are two broad categories of load pull measurement methodologies: traditional or power meter based load pull, and vector receiver or VNA based load pull. Vector receiver load pull is a modern and more accurate measurement methodology where the low loss couplers are used to directly measure the incident and reflected power waves at the DUT reference plane in real time, presenting vector information that enables computation of various device parameters such as delivered input power, power gain, power added efficiency, and others. The main frequency limitation in VNA-based load pull comes from the 67 GHz frequency cutoff of modern VNA receivers. To enable W-band vector receiver load pull, we have developed custom 110 GHz low-loss couplers with integrated down conversion circuitry that enable any VNA to directly measure the down-converted incident and reflected waves at the vector-calibrated DUT planes. Additionally, we have developed a custom signal control unit that enables accurate amplitude and phase control of the device excitation signals. The combination of new 110 GHz low-loss couplers with a signal control unit and Mori's industry-leading passive impedance tuners enables a hybrid active vector receiver load pull configuration for large signal, high-power device characterization with realizable load reflection coefficient magnitudes of 1 at the DUT reference plane. Let us have a closer look at the setup. Behind the probe station, we have an IVCAD PAV system, a Keysight PNAX, and a Mori signal control unit. The IVCAD PAV system is used to bias our device. The PNAX is configured to perform vector receiver load pull measurements with the VNA receivers directly connected to our new 110 GHz low loss couplers. Additionally, port 4 of the PNAX is used to output a signal that is injected as a local oscillator input into the integrated down conversion circuitry inside the new couplers. Finally, the signal control unit is used to modulate the amplitude and phase of the DUT excitation signals injected from the PNAX through the use of high accuracy IQ modulators. The modulated signals are then injected towards the input and output of the device under test, thus enabling hybrid active load pull measurements. On the probe station, we have two frequency multipliers to upconvert the DUT excitation signals to millimeter wave frequencies. We also have two stepped attenuators with maximum resolution of 0.01 dB for accurate signal amplitude control, input and output preamplifiers to drive the DUT on the input and to facilitate active signal injection and desired load reflection coefficient synthesis on the output of the DUT. We have two 110 GHz low-loss couplers with integrated down conversion that enable vector receiver load pull measurements at these frequencies, and a passive load pull tuner that is used to pre-match the DUT, thus enabling high-powered DUT load pull with very high reflection coefficient magnitudes. So now that we know how the setup is configured, we can perform load pull measurements.
The W-band waveguide hybrid active vector receiver load pull setup is easily configured in IVCAD, the industry's premier device characterization and modeling software suite. Immediately after starting the software and selecting a waveguide vector receiver load pull measurement option, we see a familiar user interface where each instrument can be configured individually. The VNA is configured so that one source is always available for driving the DUT on its input and for active signal injection on its output. For this purpose, we are using ports 1 and 2 of the VNA. The second source of the VNA is used as a local oscillator signal in the down conversion path of the 110 GHz couplers. This signal is generated on port 4 of the VNA. In the VNA setup window, we also need to configure the IF bandwidth of the receivers, averaging, and define the parameters of the millimeter wave frequency down conversion. Here we select the IF frequency, RF and LO multiplication factors, as well as the input, output, and LO powers. We then need to set up the signal control unit, or power handler, where we set the maximum I and Q voltages for the on and off states of the modulators. After that, we need to configure the transmitter modules on both input and output of the DUT that are comprised of the frequency up converters and step attenuators. Then, the load tuner is configured in exactly the same way as for any other local measurement in IVCAD. After that, we configure the power meter, which will be used during the system calibration, and the IV power supplies that will be used to bias our device under test. When each individual instrument is configured as desired, we can start the system calibration. We start the calibration by first performing a power gain characterization on the input network. This will enable the accurate available power control on the input of the DUT. Then we go through the same procedure on the output of the DUT. When we have successfully determined the gain of the input and output networks, we can perform the standard vector receiver calibration to establish the DUT measurement reference planes. The final step in the system calibration is to perform a power calibration. To do this, we first perform a one-port calibration at a desired reference plane and then connect the power meter at the same reference plane. This will ensure the correct propagation of the power calibration coefficient from the one-port reference plane to the two-port reference planes. With this step, we finish the system calibration. Now, before we progress to the DUT measurements, we need to perform the tuner auto de-embedding. This will shift the impedance control planes from the tuner reference planes at which the tuner was characterized to the DUT reference plane, taking into account the response of all the components that are connected in front and behind the tuner. After the tuner auto de-embedding is completed, we can see how the impedance tunable range has changed when components in front and behind the tuner were introduced. The blue region is the impedance tunable range at the tuner reference planes, and red is the impedance tunable range at the DUT reference plane. This information is displayed for each tuner characterization frequency. Now we can initialize the setup and configure our measurement. Before we measure our DUT, we need to validate our calibration. For vector receiver load pull, the validation parameter is power gain on a through connection, and we are looking for something less than plus or minus 0.2 dB at all phases of 0.8 gamma magnitude. In this case, our minimum power gain is minus 0.175 dB, which highlights a good system calibration. After this step, we are ready to perform our DUT measurement. We first bias our device, then we set the desired power sweep range. After that, we configure the impedance sweep and start the measurement. During the measurement, all the device parameters are computed in real time, listed in the table on the left-hand side of the measurement window, and plotted on a Cartesian plot. Moreover, the DUT input and load impedances are measured for each power level and plotted on the two Smith charts at the top of the measurement window. After the measurement is finished, we can easily analyze the measurement data using IVCAD's advanced data visualization tools and plot the device parameter contours against the desired gain compression value.
In summary, Mori's millimeter wave hybrid active load pull solution enables high-power device characterization between 75 and 110 GHz under linear and non-linear operating conditions as a function of load impedance. Vector receiver load pull enables the computation of various device parameters such as delivered input power, power gain, power added efficiency, while also enabling characterization of nonlinear phenomena such as frequency mixing, harmonic generation, AM-AM, AM-PM distortion, and intermodulation. With Mori Microwave's millimeter wave hybrid active load pull solution enabled by state-of-the-art hardware and software, you can overcome the direct receiver access frequency limitations of your VNA and perform vector-corrected, high-power load pull measurements between 75 and 110 GHz. For more information on this or any other device characterization solution, visit morimw.com or contact your local field engineer. Thanks for watching.